Hello viewer, welcome to Artistry. My name is Ongweso and I'm going to present a topic in electrical engineering under the topic we call performance of overhead transmission lines. To begin with, the generation of electrical energy, the transmission of electrical energy, and the distribution of electrical energy to the consumers, that is domestic and commercial users. It is majorly done on overhead transmission lines. Due to transmission, we have two factors which are of more important. So one is transmission efficiency and voltage regulation. So these are the two factors which one must consider when evaluating the performance of an overhead line. It is desirable that the efficiency of a transmission line is as high as possible. If it is possible to be 100%, it will be okay. But now, due to some line parameters, that one is not possible. But we try as much as possible to minimize the losses in the transmission line, such that the amount of energy which is being received at the receiving end is almost equal to the amount of power or energy which was being sent from the substation. Before we do this, let us study the line parameters. Line parameters, and when we talk about the line parameters, these are those elements which can cause the reduction in or interference in the transmission lines. Number one, we have resistance. If its SI unit is ohm. And this is the symbol. Resistance is the opposition to the flow of current in a system. Number two, we have resistance. If its SI unit is Henry, L. Number three, we have capacitance. Its SI unit is farads. So these are the three elements which affect the transmission of electrical energy. There are three. Now, after we have catered for all of this, we can now analyze one by one. There's what we call transmission efficiency. If you take the ratio of the receiving end power by the sending end power times 100, this efficiency is given by the receiving end power divided by the sending end power times 100%, you get the efficiency of a transmission line. It is therefore desirable if the efficiency is approaching 100%, that's when we say that the system is efficient. Another factor I have to consider is what we call voltage regulation. When we talk about voltage regulation, this is the difference at the receiving end between the conditions of full load and no load. If you take the ratio of the voltage being sent from maybe the substation minus the voltage received at the far end divided by VR times 100%, you get the voltage regulation. But this one is desirable if it is more closer to zero. Next, let us now derive an expression of voltage from the sending end using the parameters of the transmission lines. For example, we have types of transmission lines. We have types of transmission lines. Number one, we have short transmission lines. Short transmission lines. When we talk about short transmission lines, if a line has a length of less than 50 kilometers, less than or equal to 50 kilometers, we call that line a short transmission line. And if it is carrying a voltage, and if it's carrying a voltage of up to or less than or equal to 20 kilovolts. So if a line is consisting of a length of less than 50 kilometers and a voltage of less than 20 kilovolts, then we can term that transmission line as short transmission line. Number two, we have medium transmission lines. Medium transmission lines. If this line has a length of between 50 and 100 kilometers, if it has a length of 50 and 100 kilometers, and the voltage between 20 and 100 kilovolts. If these two conditions prevail in a system, a transmission system, then you can call that system as a medium transmission line. Number three, if we have this what we call long transmission lines. So if a line has a length of more than 100 kilometers and a voltage of more than 100 kilovolts, then that system we can call it a long transmission line. After analyzing these three types of transmission lines, that is the short, medium and long transmission lines, now we can derive an expression to show the relationship between the voltage sent and the voltage at the receiving end. We want to derive an expression for the sending end voltage as well as the sending end power factor of a transmission line. But let us start with a short transmission line. Short transmission line. In a short transmission line, the impact of capacitance is neglected. We don't take into consideration the effect of capacitance. So we only consider the inductance. So this is the equivalent circuit of a short transmission line. This is the load, which maybe your radio, a TV, or an industry. We have the inductance here. So the inductance we normally represent with X, and the XL is the reactive inductance. This is R. Here we have Vs, the voltage which is present from maybe the generating station or the substation. This is the current I, and it's common. But in between here we have what we call impedance Z. The summation of these two will give us the impedance Z, and under this impedance we will be having a voltage drop. So after having a voltage drop, at the end here, the end voltage, we call it receiving end voltage, VR. Using this circuit, we can come up with what we call phasor. Current is common in the circuit, so current becomes our reference. As you can see, Vs must be greater than Vr, because Vs is what has been sent and V is what has been received. So the angle between the current I, and the VR, we call it phi R. This is the angle which gives the power factor of the receiving end. The angle, the complete angle, that is from I to Vs, this line is represented by Is. We call this phi S, the angle which will give us the sending end power factor. This between Vr and Vs, we have a small angle, we call it alpha. So alpha is the difference between Vr and Vs. And Vs is given by phi R plus alpha. So here we have the voltage drop between this point. We have the voltage drop between the resistance I R. Here we have the voltage drop IXL. IXL. So if you extend this line, you will have the IZ, the combination of this and this using Pythagoras theorem. So if you can label our triangle A, B, C, D, E, F. Consider triangle ACF. Consider triangle ACF. Using Pythagoras theorem, AF squared should be given by AC squared by CF squared. But now AB is not given. Using the famous formula SOHCAHTOA if we use this sin theta, so sin phi r equals to opposite over hypotenuse. If we consider this small triangle ABE, so it will be opposite, which is BE, over hypotenuse, which is VR. Therefore, the length BE will be given by VR sin phi r if you cross multiply both sides by VR. Using this one, cos phi r is given by adjacent over hypotenuse. According to this angle, adjacent is AB and hypotenuse is VR. Therefore, if you cross multiply by this VR both sides, therefore AB will be given by VR cos phi r. Therefore, this length AB is equivalent to VR cos phi r. And this length is the same as this length is given by VR sin phi r. After getting the value or the magnitude of AB and the CD, which is equivalent to BE, we can now proceed our formula because ED is equivalent to PC. Therefore, IR is also the same as the lower case. So let us proceed from here. AF, which is this, is equivalent to AC squared plus CF squared. Therefore, AF is VS squared should be equal to AC, which is equivalent to AB plus BC. AC is equivalent to AB plus BC squared plus CF is the same as CD plus DF squared. So if you substitute these values, VS squared will be given by VR cos phi r plus this length is the same as this, so it is IR squared plus CD, which is a VR sin phi r plus IXL squared. If you can take the square root both sides, therefore VS will be given by this VR cos phi r plus IR squared plus VR sin phi r plus IXL squared. So this is an expression for sending end voltage. If you can be asked to derive the expression for sending end power factor using the same triangle, the same figure, if you consider triangle ACF, the bigger triangle, and using SOHCAHTOA, cos phi s is given by the adjacent, which is AB over hypotenuse, which is AF. Therefore, this will be equivalent to AC. It will be equivalent to VR cos phi r, this, plus divided by phi s, where phi s is the order of this thing. So in review of what we have learned today, in a summary, we have discussed that we have three types of transmission lines. We have short transmission lines, we have medium, and we have long transmission line. So it depends on the length and the amount of voltage the line is carrying. That's how we can categorize in this. At the same time, we have managed to derive an expression of phi s, sending end voltage, where we have managed to come with an expression like this: phi r cos phi r plus ir squared plus phi r sin phi r plus ixr squared. We went further and derived the expression for sending end power factor, which is cos phi s. We managed to show that cos phi s is given by phi r sin cos phi r plus I r over phi s, where phi s is the order of this thing. So we can replace here. This marks the end of the class. I'm your presenter, Dennis Ongweso. Stay tuned to Elimu TV.